All right, so this is the second hour of Physics 1A for March 15th. And we're finding, we're going to be solving this problem right here. This says the height and range of a projectile 1 batted baseball. So a batter hits a ball, so it leaves the bat at a speed of 37 meters per second. With this angle, we want to find the position of the ball and its velocity, magnitude, and direction at t equal to 2 seconds. We want to find the time when the ball reaches the highest point and its height at that time. We want to find the horizontal range r, that is the horizontal distance from the starting point to where the ball hits the ground, and the ball's velocity just before it hits. A bunch of different things we want to calculate here. All right, so let's start off by kind of drawing a picture of the situation. It's going to be pretty similar to the picture we just drew. So we've got kind of an XY coordinate system that looks like this. We have a ball that is launched from right here with some initial velocity. I guess I should actually try to draw this to the angle that it's given. So it says that the ball is batted at an angle of about 37 degrees with an initial velocity that is 37 meters per second. So this is 37. And the angle right here, which is called alpha naught, I'm probably just going to call it theta, but I guess we can call it alpha naught, whatever. Alpha naught is equal to 53 point... Oh, the angle. Sorry about this. Oops. Control Y, will that do it? Yeah. Sorry, the angle is up like this, my bad. Yeah, okay. So this is the angle. This is the initial velocity vector. Confused me because the velocity is 37. That's usually what an angle would be. Okay. Find the position of the ball and its velocity at t equal to 2 seconds. Now, I don't know where this ball is going to be at t equal to 2 seconds. I just know it's going to, it's going to fly through the air. And 2 seconds later, it's going to be somewhere, right? Do you think it'll be on the way up or the way down 2 seconds later? What do y'all think? Still going up? Yeah, probably. Probably still going to be going up. Let me, can I click on this? Can I extend it this way? There we go. All right, so we want to find where the ball is 2 seconds later. It's probably somewhere in here, but we don't really know before we do the problem, so let's, it probably is going up though. So how do we figure out where it's going to be? Well, usually what I do when I do these kind of problems is I just kind of set up a grid for what's going on in the y and the x direction like this, and I just fill out the table basically. In the x direction, what we know is there's 3 variables that we care about. There's delta x, which we don't know, but it is one of the things we want to calculate. So let's say the ball gets to here, for example. Then this would be delta x down here. We don't know what that is. We know time is going to be 2 seconds, though. And we also know that the x component of the velocity can actually be found by the given information. So if its initial velocity is 37 at an angle like this, then the x velocity, which would be the component that would be down here, we can draw a vector right here to represent the x velocity. We can also draw a vector to represent the y velocity. How am I supposed to do this that I don't get that thing? I guess I do like that. Oh, and I changed the color there. I'll fix that. So this is going to be green. Green. There we go. That one's blue. Okay, so this down here is v sub x, and then the other one's v sub y. And if you look at the triangle right here, since this angle is alpha, that means that Vx has to be equal to what? It's always going to be equal to something like V initial multiplied by, what is it? Cosine or sine? Cosine. Alpha naught, right. Okay, come over to the y direction. We're just going to write down everything that we know in the y. Oh, you know what else we could do? Is we can actually solve for what this is. So let's do that. And what I'll do as well is just, I'm going to delete this line. So v initial cosine alpha, in this case, v sub x, is going to be equal to 37 meters per second times the cosine of 53.1. Can you all calculate what that is for me? I just realized I left my other calculator in my room. I'll be right back. Okay, so 22.2. Okay. I'm going to put this in my calculator as well so I can get the full number so I can use it later. So 37 times cosine of 53.1. Yeah, I agree. 22.2. It's like 22.22. That's right. We'll put 4 digits in here so that... Okay. All right, so we've got the x direction. In the y direction, we've got a lot more variables. So in the y direction, what we've got is we have a delta y, we have a t, we have a vy initial, we have a vy final, which I'm just going to call vy, and then we have acceleration in the y direction. Acceleration in the y direction is going to be negative 9.8. Oh, I left off a step. One of the things we always have to do here, I kind of put it in, but I didn't say it. This is going to be positive x, and this is going to be positive y. All right, delta y, for this first part, we don't know what it is. The time we do know is 2 seconds. Vy initial we can calculate from here. This is going to be equal to 37 meters per second multiplied by the sine of 53.1. This one is going to be 37 times sine. So I got 29.59. Yeah, I agree. Oh, that's awful. And then Vy we don't know. Okay, so in part A of the problem, it says, find the position of the ball and its velocity at t equal to 2 seconds. So that's why I put t equal to 2 seconds in both of these right here. So to find the position and the velocity of the ball, including magnitude and direction, we're going to need to know what the x-coordinate is and the y-coordinate of the object, basically, right? So let's go through and find each of those. Let's start off with the x direction. In the x direction, we have just one equation that we can use to find what's going on. Oh, sorry, it's 29.59? Yeah, you're right. Sorry about that. Thank you.
Mr. Murdoch, what about Vx to 0, to the initial?
The x velocity never changes in these projectile problems, so I'm never going to talk about x initial or anything like that, but good question. All right, so delta x equal to Vx times t. This is your x velocity equation. We know both of the things on the right-hand side of the equation, so we can just straight up calculate what delta x is. So Vx is equal to 22.22. And we multiply that by 2. Okay, I think I can do this calculation in my head. Doesn't look too hard. I think this is going to be 44.44. And the seconds cancel out, and you just get meters. So this is delta x. And if we said that the initial position was 0, for example, like if we call this position that the ball starts from to be 0, 0, then that would just be the x-coordinate, basically, right? Okay, that's half the problem. The next thing we want to do is to solve for what's going on in the y direction here. So we use the other equation, which is basically delta y is equal to Vy initial times t plus 1/2 acceleration in the y direction times t squared. Plug in all of our numbers. We're just solving for delta y, so we're going to get delta y is equal to Vy initial, which was 25.59, multiplied by t, which is 2 seconds, plus 1/2, negative 9.8. And then, did I do it again? Oh, I erased it and then put the same number then, didn't I? Oh, yeah, I'm just cruising right along, making mistake after mistake. Okay, 29. I really appreciate that you are watching and paying attention. Okay, then this would be times 2 seconds at the end, and then we square it, calculate what that is. I got 39.58. So I think this means that our assumption was correct, that the ball is on the way up still. That's exactly 39.58. That's kind of surprising. Okay, does everyone agree? Get the same answer? So x is 44 and y is, so it's somewhere up here, maybe. Okay. Now, at that location, it also has a velocity that we need to find because we wanted to find the position of the ball and its velocity. So now we're going to have our velocity vector right here. It's going to be kind of pointing up at an angle like this. Let's make it more to scale. It should be more like that, I guess. And of course, this velocity vector is also going to have x component right here that we'll make green, and it's going to have a y velocity. We'll go from here to here. That will make blue. So that's going to be our Vy, and down here our Vx. We already know what Vx is. This is constant. It doesn't change. Does it matter if we have 9.8 as 9.81? No, that's fine. You're not going to get exactly the same answer, but you can use 9.81, sure. Okay, so in order to figure out its velocity at this point, we need to find this right here, right? We need to find what Vy is equal to, because we already know Vx. So if we knew what Vy was, then not only could we find what Vy is, but we could also find what V is right here, right? So let's do that. Let's figure out what Vy is equal to. To find Vy, we have all the same information, but we're just going to use this, time, and this to find what Vy is equal to. And for that, we need to use a kinematic equation that has those three variables, which is going to be this one. Plug in all of our information. We're going to get V sub y is going to be equal to Vy initial, which was positive 29.59. Plus the acceleration in the y direction is negative 9.8 times 2. This is going to give us Vy equal to something like 9. 9.99. Almost 10 exactly. So there's Vy, but we also know what Vx is. You can kind of see it up in the top of the screen there, that Vx was equal to 22.22. And now if you look at the way the question's asked, this is going to be relevant to your homework, because you're always going to have to read the problem and see what it's actually asking for. It wants us to find the velocity, magnitude, and direction. Okay? When they say magnitude and direction, they don't want it written like this. They want the value of the velocity here, and to get the direction, we're going to need the angle that's made right here. So let's define this angle right here to be theta, and those are the two things that we want to calculate. We want to find what this velocity is, and we want to find what this angle is right here. So how do we do that? How do I find what the velocity magnitude is up here? Sorry for crunching all this stuff in, but I don't know what else to do. What I could do is take this work, kind of shift it over some, and make it smaller, I guess. Yeah, that's right. You basically use the Pythagorean theorem. We can say that the magnitude of the velocity vector is going to be equal to Vx squared plus Vy squared square root. Now you can see the numbers over here, so I'm not going to type them in. I'm not going to write them on the board again. We'll just take the numbers that are over there on the left. 9.99 squared. All right, I should write it out, actually. I shouldn't skip steps. I'm always struggling between wanting to do more and wanting to show every step. That is the constant struggle with this class. Is I would always love to do like 20 examples every class, but then I wouldn't be able to explain everything, and I wouldn't be able to show all the steps. So I know that having all the steps is important for everyone. Okay, so we do that squared plus 22.22 squared. Take the square root of all that. What'd you guys get? 24.36, I agree. So that's the magnitude of the velocity. I'll scroll down as soon as I finish writing this. Okay, and then what about finding the angle right there? Sorry, it's kind of off the screen. You can zoom out just a little bit. Let's keep it on the screen. And then do this. Go up just a little bit. How do I find the angle? Right here. Yeah, we're going to use the arctan of Vy over Vx. So that's going to be the arctan of 9.99 divided by 22.22. And we're not going to worry about the units because those will cancel out from this ratio right here. So you end up getting theta is equal to arctan 24.2 degrees. Okay, so the velocity, we write it like this. The velocity is equal to 22.36 meters per second at 24 degrees. We'll just write it like that. And by 24 degrees, we mean above the horizontal. And that's the solution to just part A. There's a lot of steps to this problem. That's just part A. We had to find the position, which was going to be x and y. And we had to find this down here. Does anyone have any questions about anything that I did? Oh, the velocity. I didn't write it down right, did I? Why did I write a 2 right there? I don't know. I don't know. But I did. That is a 4. I apologize for that. Thank you, Raina and Kelvin. The rest of it's okay, though, right? I think it's okay. Let's look at the numbers. The angle was 24.2, and the velocity was 24.36. So we got to change it in the answer, too. Right here. That should be a 4. Okay. 3:38. Took us 18 minutes to do one part of this problem. All right, so let's keep going. The next part says, B. Find the time when the ball reaches its highest point of flight and the height h at this time. So we need to find the time that it takes to get to right here, basically. Okay? Since I had to scroll down so far, what we'll do is we'll say, just kind of start a new problem. We'll say this is part B. Those are the two things that we want to calculate. The way we're going to do this, this process that we do these things with is going to be very repetitive every single time. So I'm going to write down some information about the x direction. I'm going to write down some information about the y direction. And we'll use whatever we've got to solve our problem. Okay. X direction, what do we know? Delta x now, even though we solved for something in the previous part, we're trying to find the time that it takes to get to the maximum height, right? So now we're trying to find this time right here. And delta x now is going to be this new delta x. I'm sorry, what's wrong, Kelvin? Is everything okay? You put a lot of dashes there. Okay. I hope I wasn't confusing you. Okay, so we're trying to find the maximum height, right? So this is max height right here. And we've got a new delta x, right? So this is a brand new quantity. Velocity initial, though, is the same as it was in the previous part, right? So the initial velocity was this quantity right here, or the x velocity is this. That doesn't change. That was the initial x velocity. It doesn't change. We can just copy that one down here. The time is what we're looking for, so we don't know what the time is. We look at this information and we say, that's not very much, that's not very good, but this doesn't really tell us anything, right? Which is 2 unknowns, 1 known. We can't really do much with that. In our y direction, we know we want to find delta y. That's going to be what we call h max. That's going to be the maximum height. We do know the initial velocity in the y direction. Okay, from the previous part, that was this quantity right here, 29.59. That's not going to change. We can write all the rest of our variables down now. So Vy is something we can talk about. Ay is going to be negative 9.8. And T we don't know. Okay. So in order to solve something in this problem, we need one other piece of information. It's going to come from here. What is the y velocity going to be when the ball gets to the top right here? Yep, the answer is 0. The ball briefly comes to rest in the y direction when it gets to the top. Okay, the y velocity at the top is 0. That should give us the information we need to solve really for anything that we want here. Okay, so let's start off by solving for time. To solve for time, we need an equation that has this variable, this variable, this variable, and time. Okay, if you look back at your kinematic equations, when you're doing these kind of problems, you'd want to have kind of them handy. Then you're going to find that there's this equation, Vy is equal to Vy initial plus acceleration in the y direction times time. That has the 4 variables that we want, right? So we now want to solve for t, so we'll do that by isolating time and then plugging in the equation, or the variables. So Vy was 0 minus Vy initial is 29.59. And acceleration is negative. If you do all this right, you'll never get a negative time. You never want to get a negative time. So this is going to give us... Let's see if I can actually transpose from my calculator properly here. I got 3.02 seconds. All right, we've got that. And now we can figure out the maximum height, because delta y, right? Now, ideally, what you want to do here to find the maximum height is you want to use a new equation, and this new equation you're going to use needs to have delta y, Vy initial, Vy, and Ay, but not t. We just solve for time. You don't really want to use an answer you just got, because if you're like me, you're going to make mistakes and you're going to write things down wrong. So instead, what we'll use is this equation. Oh, let's use black or something so that's easier to see. Stop it. All right, then we'll use this equation. Vy final equal to Vy initial. Sorry, we're not using this notation, are we? We're just calling it Vy, to avoid using so many subscripts. So this one, Vy squared is equal to Vy initial squared plus 2a delta y. And this is a sub y. And we want to solve for delta y. That's going to be what we call h max, basically. So rearranging this equation, we're going to get Vy squared minus Vy initial squared divided by 2a. That should be equal to delta y, which is what we're calling h max. Plugging in the numbers we have, it's going to be 0 squared, which is obviously 0, minus the initial velocity in the y direction, which is 29.59. And then divide by 2 times negative 9.8. Again, you'll see that the negative signs are going to cancel. You're going to get a positive number out of this. So we get 29.59. We square that and divide by 2, divide by 9.8. 44.67 is what I got. So I get that delta y, which is also equal to the maximum height, is going to be equal to there we go. Now you can also, if you want to, move this way down because we're going to need some more room. Another thing you can do is if you look at this equation right here, there's actually another way that we can write it. So delta y is equal to, this was 0, minus Vy initial. We have this other way of writing that, right? Which is V initial multiplied by the sine of the initial angle, which in this problem it was called alpha naught, so we'll use that. This whole thing gets squared, and you divide by 2 times negative g, because the acceleration in the y direction is negative 9.8. And then this expression then looks like this. You get v initial squared, sine squared alpha initial, which is the initial launch angle, divided by 2g, and this is your maximum height. And that is a perfectly general result that you should be able to use in a lot of your problems. You should also be able to derive it. It's not hard to derive, but that's in general what the answer is. Okay. So there we go. That was the time, and that's the height. Anyone have any questions? This problem takes so long. Last, C, find the horizontal range, R. That is the horizontal distance from the starting point to where the ball hits the ground. And, of course, you gotta have like 15 parts to this problem. The ball's velocity just before it hits. Horizontal range. Okay. So now what we're looking for. Do you need to prove this every time you want to calculate it? I would say no, but you should be careful about it. Be careful about when you use it. All right, part C says max range, which is going to be the max horizontal range. And what was their part? Oh, the velocity before it hits. So now we want to find those two pieces of information. Now, there's two different ways we can do this. One way would be to say, well, if this is the time that it takes to get to maximum height, right? What's the time that it's going to take to hit the ground? Max horizontal range would mean that basically the object is launched from here, and it goes through the air and it lands here. That's going to be the range, r. Yeah, 2 times the time. So we could basically say the time that this is going to take is going to be double the time. So that's one way you could do it. I'll leave that to you all to do it that method. I'm going to do it in a different way. So in this problem, we can once again split things up into x and y. Delta x is going to be the thing we're looking for, which is r. The time, let's just say we don't know what it is. Wouldn't the velocity before it hits be the same as when it was hit? Yeah, that's right, Andrew. We're gonna prove that basically right now. That's right, Andrew. Exactly. We're gonna prove that that's true with math. So we saw that it was true like from the simulation. We want to prove it now. So delta r, we're just gonna call delta x. We're gonna call r. We're gonna assume we don't know the time, and the initial x velocity. Well, that's still the same as it was before, right? Which was 22.22. Okay, y direction, let's use a different color. It didn't notice that I did that. So y direction, we got delta y, we've got ay, which is negative 9.8, or just negative g, which we might use. Vy initial is 29.59. We don't know t. One of the things we're going to try to find is Vy. Okay, we've got all our information. We can start a new problem right here. Again, I'm going to have to move this down even farther. Okay. All right, so our goal is to find the range, okay? And what I'm going to do is I'm going to solve for the time first, okay? And we're going to do it symbolically. We'll put all the answers in at the end because just knowing the range answer is going to be helpful to us and the equation we can use for it. So the first thing to ask is, what is delta y going to be when an object is launched and then it lands at the same elevation that it launched at? What's the change in the y-coordinate if this is the y direction? It's 0, right? That's right. Good job. So if it starts off at 0 and it ends at 0, delta y is just 0 minus 0, which is 0. Okay, so that's kind of helpful because then what we can do is we can solve for the time. And we can do that by saying, I guess I'll write it over here. Delta y is equal to Vy initial. Now, Vy initial in terms of symbols, because I want to do this in terms of symbols. Before was V initial times the sine of alpha naught, right? Just to draw it on the picture here, this was your V initial vector, and this was your alpha naught vector, or your angle, sorry. So then Vy initial is going to be V initial times the sine of alpha naught, multiplied by t, and then minus 1/2 gt squared. Right? This was an equation that we wrote down earlier when we were talking about projectiles in general. And okay, so the delta y is 0 in this particular problem. So we can rewrite it like this. We can add the 1/2 gt squared to the left-hand side. So you get 1/2 gt squared. Actually, no, let's do this the right way. Let's do this the actual right way. So if I want to do this properly, what I do is I pull the time out, and I get an equation that says V naught times the sine of alpha naught minus 1/2 g times t is equal to 0. This means you have two solutions for the time. The time can either be equal to 0. At t equal to 0, the ball is here. That's one time when the delta y is 0. Or you get the other solution, which is that the time, you get it from this equation right here, should be equal to 2 times V initial times sine alpha naught divided by g. Okay, just basically what you need to do is, all right, I shouldn't have done that. Sorry, I skipped a step again. So when you have something that's t times something else that's equal to 0, you have two possibilities. Either t is 0 or the other thing is 0, which means that we can set this other piece of the equation to 0. V naught sine alpha naught minus 1/2 gt. You can set that equal to 0. And if you do that, add the 1/2 gt over here, and then isolate time, you should get this. I think. Everyone agree with that? Next thing to do is to then use our x information. So in the x direction, what we know is that delta x is equal to Vx times t, or V initial times cosine alpha initial multiplied by time. So delta x then, which is what we're calling r, we'll just call it r, should be equal to V initial cosine alpha initial times the time. So we'll plug this in. So 2 V naught sine alpha naught divided by g. And now we're just going to simplify this a little bit. So we're going to use one of the double angle formulas. The sine of 2x is equal to 2 times the sine of x times the cosine of x. Does that look familiar to most of you? You may not remember it, but I'm sure some of you do. If you don't, that's no big deal. So we're just going to use that to write this in a simple form. We're going to write it as, so you've got V naught squared, right? V naught times V naught. And you've got the 2 sine alpha cos alpha. These are both alpha naught, sorry. So this is going to be the sine of 2 alpha naught. Oops. And then we're going to divide that by g. I just want to compare real quick because, yeah. This one has a 2g in it. So this is V naught squared sine squared alpha naught. This one is V naught squared sine 2. Yeah, this looks right to me. I'm pretty sure that's the right equation. So that should give the max range. Okay, and this is a perfectly general equation, but keep in mind that this equation is only going to apply when the object is launched and lands at the same elevation. Okay, and we're going to use this to prove some of the things we saw in the previous thing. So what is it actually equal to in this case? Well, we would take V initial, which was, now we got to go way back. What was V initial equal to? 37. That was our initial velocity. And the launch angle was 53.1, right? Yeah. Okay. So plugging everything in, you get 37 meters per second squared, and then the sine of 2 times 53.1 divided by net. This is just 9.8, by the way. Don't get confused that you should put a negative sign in. Anytime I write g, I mean just this number. And so for this problem, that horizontal range is going to be 37 times 37 times the sine of 2 times 53.1. We divide all of that by 9.8. We get 134 meters. 134 approximately meters. That is our range. This is the max range equation. Any questions? All right, now, we saw when we were doing the, go ahead and keep typing your question, Ton. We saw when we were doing the thing with the PhET simulation that when you launch something at like 2 angles that added up to 90, you got the same range, right? So let's see why that's the case. Let's say that I take, for example, the sine of 2 times, let's just use what we used before, 65. And you do also the sine of 2 times 25. And you put those in your calculator. I'm pretty sure you're going to get the same answer. So if you do the sine of 130, and you do the sine, I got 0.766. And you do the sine of 50, you get the same answer. And I think it's because if they add to 90, what's going to happen is that, I don't want to go into more detail. We got to keep moving. So you can do some more math to prove why this is true. Basically, if you just put sine of x and the sine of x plus 90 and just work it out, you're going to get something that it'll make sense why it works out. Not x plus 90. 90 minus x. All right, was there another question? Oh yeah. The last part we wanted to prove was about the velocity, because we also wanted to find the velocity of the ball just before it hits the ground. So in order to do that, we just need to use our set of information here, and we're going to find what Vy is equal to. Now this is really easy to prove. I could almost prove it up here, actually, in this little space. Right here. Yeah, it's going to look awful. Never mind. Delta y is 0, right? So watch how easy this is to prove. Vy squared is equal to Vy initial squared plus 2a delta y, right? But this is 0, right? So that means that Vy squared has to be equal to Vy initial squared. Now there's two possibilities for this. Either Vy is actually equal to Vy initial, or what's the other possibility? Yes, Tom, that's right. We already talked about that. That's right, but that's right, yeah. What's the other possibility that can make this equation true? Yeah, negative Vy initial. So the other possibility is that Vy is equal to negative Vy initial. That basically proves it. That's the answer, actually. Because we know that the ball is launched upwards, so it has a positive y velocity component, and when it hits the ground, right before it hits the ground, it has a negative y velocity component. Okay? So there we go. It took us 40 minutes to do that, bro. It's amazing. I know I could do this faster in the classroom, by the way. I know for a fact I could, with all the moving around and all that kind of stuff. I could have done this problem probably in 25 minutes, but anyway. So we got to take another break. That'll leave us with a nice chunk of time to finish up doing some harder problems. I do have harder problems. I know this one isn't that hard, but we will do things that are a little bit more challenging. So the next problem we're going to do is this. I don't know if I even want to do this one. This one might be too simple. I think it's worth doing, though. I don't want to ramp up the difficulty too quickly. But so we're going to take a break. We'll take a 10-minute break and look at this problem. And if you want to, try to start solving it.